A quick recap of what we saw yesterday. We talked about second order non-linearity, and remember that we are only concerned about weak non-linearity. So, V out is some A 1 V I plus A 2 V I square plus higher order terms. Yesterday we considered only the case of second order non-linearity, and when we said weakly nonlinear, it basically means that A 2 V I square in magnitude is much smaller than A 1 V I in magnitude, right. So, we saw the phenomenon of intermodulation, where two different tones basically get multiplied with each other. So, if you have two tones of at frequencies f 1 and f 2, you not only see the harmonic distortion components, namely at 2 f 1 and 2 f 2, but you also see f 1 plus f 2 and f 1 minus f 2 in addition to some DC offset, right. And then we finally looked at fully or differential circuits, and one of the important consequences of differential operation is that all even order distortion terms are eliminated. So, in many practical systems, it is only the third harmonic or third order nonlinearity is very problematic. Okay, and that is what we are going to see today. In other words, V out is A 1 V I plus A 3 V I cube plus higher order terms. We assume that the higher order terms are negligible compared to A 3 V I cube, and weak nonlinearity basically means that A 3 V I cube is much smaller than A 1 V I. All right. So, as usual, let us see what happens when you put in a single tone first. So, V I is say A cos 2 pi f 1 t, and therefore, V out is nothing but A 1 A cos 2 pi f 1 t plus A 3 times A cube cos cube 2 pi f 1 t, and let us recall the following trigonometric identity. Cos 3 theta is nothing but 4 cos cube theta minus 3 cos theta. So, this is basically a 1 a cos 2 pi f 1 t plus a 3 a cube times 3 cos 2 pi f 1 t plus cos 2 cos cube is nothing but
minus 3 cos.
Now, we are trying to replace
Cos. Oh, yeah, yes. Correct. 3 cos
Right.
theta plus cos.
plus cos 6 pi f 1 t divided by 4. All right. And so, this is nothing but a 1 a plus 3 a 3 a cube by 4 times cos 2 pi f 1 t plus a 3 a cube by 4 cos 6 pi f 1 times t, right. So, this is basically the fundamental, right, and this is the third harmonic. And it turns out that many practical nonlinearities will have, for example, if this is a perfectly linear, you would have seen a characteristic like that, right. So, this is V I and this is V out, for instance, but in practice what happens is that many practical I/O transfer curves which have only odd harmonic distortion behave like that. So, what comment can you make? So, this is basically a 1 V I, right, and this is a 1 V I plus a 3 V I cube. So, what comment can you make about the sign of a 3 versus sign of a 1?
Both will be same. Like both in the same chord. It's like if you apply.
No, man. Is V I positive or negative there?
Yeah, in the first quadrant positive.
Positive. Yeah. So, if this is a V I plus a 3 V I cube, and is that smaller than a 1 V I or larger than a 1 V I, the blue curve?
Smaller.
Smaller. So, if that has to be smaller, what comment can you make about the?
A3 has different signs.
Yeah. So, basically in many practical circuits, the sign of and A1 are different, right, and such a nonlinearity is called a what's called a compressive nonlinearity. Does that make sense? So, first things first, so let us see what we can make, what sense we can make of so if I plot the amplitude of V in on the log scale, and let us first plot the amplitude of the fundamental. Right. So, what comment can you make about the amplitude of the if you draw the amplitude of the fundamental, you will get a straight line, do you?
Slope of
No, think carefully. This is the amplitude of the fundamental. So, as you keep varying A, remember which is going to be the dominating term?
and A1, A3 are like A3, A1 is much smaller than the
A3?
like A1A is the dominant term.
Yeah, A1A is going to be much larger than 3A3 A cube by 4. So, for small for very small amplitudes, you basically will have a line which basically goes at with a slope of +1, correct. Now, as you keep increasing the input amplitude, what comment can you make? Remember that A3 and A1 have opposite signs.
The slope of 3.
No, as you keep increasing, so if A3 was 0, then this would keep continuing on forever. So, if A3 is non-zero, what do you think will happen? As you keep increasing A, at a certain point this A3 times A cube will no longer be negligible compared to A1A. So, what you will actually see is a curve which does this, right, and as you keep increasing amplitude, what will happen is that it will tend to start doing this, right. Why? Because at these, I mean beyond certain amplitude, you basically that 3A3 A cube by 4 cannot be neglected, right. So, the fundamental amplitude itself is no longer a straight line with a slope of 1 dB per dB. Okay. Technically, even at very low amplitudes, it is not a straight line, right. But at those amplitudes, that 3A3 times A cube is so by 4 is so small compared to A1A that for all practical purposes it looks like a straight line, right. So, therefore, this is so as you can see the effective gain, as you if you want to think about it that way, which is the slope of this characteristic, keeps decreasing as you keep increasing the input amplitude, right. So, this is what is called gain compression. And what this means is that the gain experienced by the input gets smaller as input amplitude increases.
This is like because of compression non-linearity only.
This is because of compression non-linearity, correct.
A1 and A3 are
Of the opposite sign. If A3 had had the same sign, then you would have an expansive output, correct. So, so one metric to basically see what happens to or rather one metric to gauge how linear the amplifier is to look at when this, when the deviation from the straight line reaches a certain value, right. If it was perfectly linear, the blue curve will never deviate from that red line, which has a slope of 1 dB per dB. If the A3 is finite, then there will be a deviation. So, people just came up with some metric. They said, well, let's kind of quantify for what input amplitude the output amplitude of the fundamental deviates from that straight line by 1 dB, right. And so, this is basically, this is called the A minus 1 dB, where that minus 1 dB indicates that for this value of amplitude, the amplitude of the output is basically smaller than what would be obtained from an ideal linear amplifier by 1 dB, right. And how do you find that A minus 1 dB? Well, ideally you should see A1A, you're seeing plus 3 by 4, plus 3 A3 A cube by 4, and therefore the deviation is this is the deviation. So, 3 by 4 A3 A minus 1 dB the whole cube must be whatever, right. 1 dB is 10 to the power so this is 1 minus 10 to the power minus 1 by 20, right, and times A1 times A minus 1 dB the whole square, not whole square. So, this is what you would, this is the linear output, right, and actually so this would basically be this is basically that guy there, correct. So, A1 times A minus 1 dB is that chap. Do you understand? This is A minus 1 dB, correct. So, this is on the red line there would have been A1 times A minus 1 dB, and we want the blue curve at that point is 1 dB lower, correct. It has to be 1 dB lower. So, 1 dB lower is basically 10 to the power minus 1 by 20, correct. So, the difference between the two is basically A1 times A minus 1 dB times 1 minus 10 to the power minus 1 by 20 is 3 by 4 A3 A1 dB whole cube. So, you can go and do the math, and then this will give you the formula for A minus 1 dB, right. And obviously, as the A minus 1 dB or the 1 dB, this is often also called the 1 dB compression point, right. And all that this means is that if the 1 dB compression point is much higher, then the amplifier can handle a larger input amplitude before it goes into before it starts to before nonlinearity starts to have deleterious effects on the output. Now, of course, the question is what will happen if you go on increasing the input amplitude beyond the 1 dB compression point, right? Well, then it's very likely that the amplifier is already not merely in the weakly nonlinear region anymore, and then it can do all sorts of things, right? So, we do not know what, and we would like, typically you would like to operate somewhere in that region, where compression is not significant. Okay. So, the next thing that we will see is there is also a harmonic distortion term. So, as we did yesterday, HD3 is simply the ratio of the amplitude of the third harmonic to the fundamental, and that as you can see is A3 times A cube by 4 . This is the amplitude of the third harmonic divided by A1A, and there is actually also another term there, but that is so small, hopefully, that is so small that can be neglected. And therefore, HD3 is simply A3 A square by 4A1, right. And yesterday we saw that the amplitude of the second harmonic component was proportional to A square. Today we see that the amplitude of the third harmonic is proportional to A cube, and that makes sense because Vi cube basically means that you are multiplying the input with itself like thrice, and therefore you get A cube, right. And since HD3 is the amplitude of the third harmonic is proportional to A cube, it follows that the ratio of the third harmonic to the fundamental becomes goes up as A square, right. So, 1 dB increase in input amplitude A will result in 2 dB increase in HD3, I am sorry, all right. And so, therefore, if I plot the strength of the third harmonic, well, that will basically go up like this, right, and that slope will be, this is the fundamental, and this is the third harmonic, and this slope is 3 dB per every dB increase in the input. Does it make sense?